Hi everyone, in this lecture we are going to start new module related to internal forces of a beam. Okay, in module 5 we have introduced that there are three internal forces in a beam, okay, which is axial, right? Axial force, shear force, and moments. Okay, and this internal forces, axial, shear, and moment, is the effect that is internally occur at a beam that is properly constrained from its rigid body motions, and then it is subjected to applied loads. Okay, so I repeat again. So these internal forces is occurred internally at a beam that is properly constrained from its rigid body motions, and then it is subjected to applied loads. Okay, and then in this module we will learn how to calculate these internal forces, axial, shear, and moment at a specific location, right? At a specific location, and also along the beam. Okay, for the second purpose, right, we are going to develop what we call as the internal forces diagram. Okay, so we have two main purposes in this module. One is to calculate the internal forces at the specific locations at the beam, okay, and then second is to calculate the internal forces along the beam, so it has to be continuous. Okay, and for this purpose we have to develop the internal forces diagrams. Okay, and the main objective in calculating these internal forces is we would like to find what are the maximum internal forces and where is it located, and these informations will be very helpful in terms of designing the beams that you guys that most of you will learn in a more advanced class, such as deformable body or mechanics of materials class. Okay, one thing that I would like to say in the beginning in here is that when we talk about internal forces diagrams, I'm going to introduce two methods. One is using the equations, and then second is using the relations. Okay. Later you will find out that this first method using the equations can be applied to any case that you want, and these relations in fact it can be applied to any case that you want, as long as you can calculate the area under certain shape. Okay, so before we start discussing how to calculate the internal forces at the specific locations and across or along the beam, we have to first agree with the sign convention that we will use in here. Okay, so for example, I have the beam right here. Okay, I have this beam, and then I make a cut somewhere in here. Okay, then I can draw this piece right here on here. Okay, and then I can draw this middle piece right here to here. Okay, and then I can draw this right hand piece to here. Okay, so remember, once we make the cut, we see the internal forces, right? And since this is a beam, there are three internal forces. We have moment, okay, and then we have axial force, right, and then we have shear. Okay, on the other side we have the same moment, right, and then we have axial force, and then we have the shear. Okay, and notice the directions of this moment right here. When I combine this left hand pieces together with the middle piece over here, it will cancel out each other. Similar things with the shear. Okay, in this left hand pieces it's going down, in the middle pieces on the left hand side in here is going up. Okay, so when I combine those two pieces together, it will cancel out each other. Okay, and then similar things with the axial force. In the left hand piece over here is going to the right, and then on the middle piece, left hand side, is going to the left, such that when we combine it together, it will cancel out each other. Okay, so and then I think it's good to call this as a left hand free body diagrams. This is middle free body diagrams, and this is the right hand free body diagram. Okay, and then to sketch the internal forces in the right hand free body diagram right here, it will go this way, and then it will go this way. Okay, same thing in here, it has to be on the opposite directions but has the same magnitude. This is M, this is N, and this is V. Okay, and note that all of these force and moments are actually occurred at this point. I just draw it a little bit far away for clarity. Okay, and one thing that I would like to say, that all of the direction that I draw in here are the positive sign conventions. Okay, so all of the direction that I draw in here is the positive sign conventions, for the reason that I will describe next in here. Okay, so for the axial force, right? For axial force, we have learned that if we have this member, right, and we have force that is going away from that members, we call that as a tension force, right? And if we have forces that is going to the member, we call that force as a compression force, right? Okay, and if this member in here is a cut of a middle free body diagrams, as what we have drawn at the top right here. Okay, on the left hand free body diagram, you will see that if in the tensions, this force has to going that way, right? Going to the right, right? On the right hand free body diagrams, this force has going to the left, right? And then for a compression force, on the left hand free body diagrams, it has to go to the left, right? And then on the right hand free body diagrams, it has to go to the right. Okay, such that if I combine this force and this force together, it will cancel out each other. If I combine this force and this force together, it will cancel out each other's. Okay, and similar to what we have learned in the previous lectures, that in tensions, tensions is a positive sign. Okay, when a member has a tensions, we have a positive sign, and when a member is under compressions, we have a negative sign. Okay, and that is the reasons I mentioned earlier that the N that I draw in here, all of them are in positive sign convention. Okay, right, then let's look at shear. Okay, the positive sign conventions that we agree on for the shears will be derived based on the middle free body diagram, so it's similar to the axial force. Okay, so we have a positive shear if the couple that occurred at the middle free body diagrams, okay, produce a clockwise moment. Okay, it's produce a clockwise moment. Then in this case, we have a positive sign convention. Okay. On the other hand, if the couple that happen on the middle free body diagrams has a counterclockwise rotation, right, then in here we have a negative sign convention. Okay, right? Since in here the force is going up, then at the left hand free body diagrams the force has to go down, okay? And similar, since this goes down, on the right hand free body diagrams has to go out, such that when I combine this force together, it will cancel out each other, right? This will cancel out each other to this, and then this will cancel out each other to this, right? In a similar reasoning, for the negative sign conventions, this force has to go up, okay, such that when I combine this force and this force, it cancel out each other, okay? And then this force has to go down, such that when I combine this force and this force, it has to cancel out each other, okay? And this is the reason why I mentioned earlier that the direction that I draw in here right, all of them are in positive sign convention, okay? And finally, let's proceed to the last one in here when we talk about moment. And for moment, the positive sign conventions that we agree on is when the moment that acts on the middle, at the both ends of the middle free body diagrams, will cause the beam to bend like this, okay? Right? So it's like people smiling, right? Like a smiling face. So in here we have a positive sign convention, okay? On the other hand, if we have couples that act at the both ends of the middle free body diagrams, that cause like a sad face, so in here we have a negative sign convention, right? And with a similar reasoning that we have done for this shear and axial, on the left hand free body diagram, the positive sign conventions in here, it has to go counterclockwise, such that when these moments are combined together, it cancel out each other, okay? And then on the right hand free body diagrams, it has to go clockwise, such that when I combine these together, it will cancel out each other. And note that all of these in here are positive sign conventions. No matter whether it's clockwise or counterclockwise, it's still positive sign conventions, because the baseline that we use to determine the sign conventions is the one at the middle free body diagrams, not whether it's clockwise or counterclockwise, okay? And then similar things for the negative sign convention in here. On the left hand free body diagrams, the moment has to go clockwise, such that when I combine this moment, it will cancel out each other. And then on the right hand free body diagram, it has to go counterclockwise, such that when I combine this moment, it will cancel out each other, okay? And that's the reasons I mentioned earlier that all of the moment that I draw in here, right, are in positive sign conventions, okay? So in most of the time when you solve problems, I would like you, and I strongly suggest you to draw your free body diagram in positive sign convention, okay? So draw your free body diagrams in positive sign conventions, and most of the time we will deal with either the left hand free body diagrams or the right hand free body diagrams, okay? So when you draw the left hand free body diagram, this is the positive sign conventions, right? And then when you draw your right hand free body diagrams, this is the positive sign conventions, okay? We will in a very rare case, we will use the middle free body diagrams, but that will be in a special or very rare case that we will use that. Most of the time, we will use either the left hand free body diagram or the right hand free body diagrams, okay? Because that's what we need to solve the problems, right? I think that's it for this lecture, and please let me know if you have any questions, and thank you for listening.